of awards and accolades, so it'll take me a while to get to so we're very lucky to have Professor Nico here. Nico obtained his bachelor's from Washington University in St. Louis in 2003. All the best people went there. He got his PhD in physics at Penn State in 2008. He was then at Princeton and then an Einstein Fellow at MIT Harvard. He was then at Montana State from 2011 to 2019. And in 2019, he became the founding director at the University of Illinois Urbana-Champaign Center for Advanced Studies of the Universe, which is a pretty cool place. Nico is known across various realms of gravitational physics, particularly for deep work on testing Einstein's theory of general relativity. He created the parameterized post-Einsteinian framework, which is basically used in most, if not all, papers on the subject. And he's also known for explorations of universal relations between observable properties of neutron stars, which is something that impacts my personal work all the time. So Nico is an expert in far more than I would list here, and also has many more awards than I was able to list here. So please help me welcome him, and we're excited to thank you, Nico. Thank you.
Good afternoon. Thank you so much for coming, and thank you very much for the invitation, and others. To come here, it's my first time here in Toronto. It's my first time in CITA. It's been a wonderful time interacting with you all and talking about super interesting science. So, as Rick said, I work on a lot of things, and I've been working on a lot of things for about 2 decades. And the reason that I am able to be here, standing in front of you, is because of all the help that a ton of other people in the field have provided and have made me into the physicist I am today. And these people are spread around all over the world. I happen to be based here, so this is my Copernican principle. But great science in lots of different places. I am very proud to be the mentor to a large group of students. Here there's mostly grad students, a few postdocs, some undergrad students. And a lot of the work I'm going to be telling you today about is work that the students do. So I'm here to represent them. So as Rick mentioned, I work on a variety of different topics, including mathematical physics, theoretical physics, phenomenological physics, computational data analysis applied to physics. So you see the underlying common denominator here is physics. So I apologize, I'm not an astronomer. I know, I have flaws. But I'm going to try to do my best to explain how the kind of gravitational physics that I study, that I'm interested in, impacts astronomical work that is done here. So in general, I would divide my work into gravitational physics that affects or relates to tests of GR or probes of beyond Einstein physics, gravitational physics that maybe has something to do with high energy physics in the context of mostly dark matter, and gravitational physics that has to do with or connects to nuclear physics. And this last topic is what I'm going to be covering in this lecture. I'm going to sort of ignore everything else, because otherwise it will take too long. So, the main point of this talk is to describe some of the things that I've been interested in studying lately related to extreme matter and what we can learn about extreme matter from gravitational wave observations of neutron star mergers. So why is now a perfect time for this? Now Rick told me, don't give a clock. He said, we are CITA. You can provide more details, be a little bit more intense. So I only have like 2-3 slides of like non-intense things, so I'm sorry. You've all seen this, but it's sort of compulsory for me to show you an animation made of the merger of 2 neutron stars, roughly 1.5 solar masses each, colliding at about 1/3 the speed of light. In 2017, coincidentally, the day I happened to organize a workshop at Montana State University on precisely what physics could we learn if one of these things were observed. Needless to say, my workshop was a complete disaster because once that got observed, everybody proceeded to completely ignore what was happening at the workshop, and they were typing frantically. Well, the lack of people were typing frantically on their computers. Everyone else was trying to figure out what the LIGO people had just discovered. This is the GW 1717 event, about 30 megaparsecs away, 40 megaparsecs away. SNR, signal to noise ratio of 30, very, very loud. Okay? It was then detected electromagnetically in essentially all wavelengths, and I'm sure you've heard plenty of talks about this. This is just a proof of principle that events like this exist. This is not the only neutron star merger that LIGO has detected, and we hope that many more will come in the near future. I'll tell you a little bit more about that in this talk. So I've divided the talk into three main topics. One, stealing title of one of Rick's previous talks. I'm going to tell you a little bit about what happens when gravity waves. Then I'm going to tell you a little bit about how and why gravity or gravitational waves encode the properties of matter. And then I'll tell you a little bit about how we're planning or hoping we can go beyond what has been done so far in terms of understanding the neutron star equation of state. Okay? So let me begin with an introduction, mostly for the grad students, about what gravitational waves are. Now, I tend to define this regime of extreme gravity as a regime where the gravitational interaction is both simultaneously very, very strong, but at the same time highly dynamical. Gravitational waves, as you know, are wave-like perturbations of the gravitational field that's measured very far away from the source. So wave-like solutions to the linearized Einstein equations. They're generated through the acceleration of masses, from a mathematical point of view, through the temporal variation of the multipolar structure of the spacetime, if you want. And then they travel at the speed of light, decaying as 1 over r, because they're really potentials, not fields, like in ENM. And they're very weakly interacting, which is also why they're so hard to detect. There's a little animation made by a former student of mine who's now a postdoc at Lawrence Livermore National Lab. Two little black holes here, 2.8, 7.2 solar masses each. That's why they're black. Here you see the orbital separation as a function of time in seconds. That says something. So these are like, tens of milliseconds. This is the gravitational wave strain, the last bit of the gravitational wave strain. You see here the orbital velocity, it's a function of time, and the frequency of the gravitational wave as a function of time. So it's chirping up, producing this sound that I cannot play, because otherwise there's going to be a feedback, like it goes like, more or less. But, if it's a circular one, then there's no beats, so just smooth. So the velocities are between 0.1 and 0.3 the speed of light, and the orbital separations probe in hundreds of kilometers. Okay. Now, how are they detected? I'm sure you've seen this before. This is a representation of interference from a planetarium show that we created for an outreach event. Here you see a Michelson interferometer that's locked. You know what that is, I can tell you about it later. But as the gravitational wave goes through, it changes the proper time of travel of photons between one arm and the other, which sometimes people depict as a stretching of space. And so your interference pattern here that was locked in a dark fringe now will oscillate and go constructed, and then very smart experimentalists have to figure out how that voltage that you measure here converts into a gravitational wave that presumably produced that signal by studying the response of the instruments to an impinging gravitational wave. So how do we extract that information about that gravitational wave from the data? How do we learn what produced the gravitational wave? So here's a representation of the straight noise as a function of frequency for 4 observing runs, 01, 02, 03, the 2 03s, 04, and then what we hope, or what LIGO people hope they can do for 05, which hopefully starts 2 years from now, 3 years from now, somewhere around there. Currently 04 is still going on, and it will end at some point this year. Looking at the LIGO people. So this is the Fourier transform. You can think of it as a Fourier transform of the data in some sort of time window. And there could have been a gravitational wave present in this in this figure. But the problem is that the wave itself could have a much smaller amplitude and be buried in this noise, and so you have to sort of extract it in some way, and the way we do that is through something called match filtering. So, in Montana, this was very clear, because everybody is used to panning for gold in Montana. You just create a filter of what you think the gold nugget look like, and then you go to the river with your little hat in your faculty orientation, and then you try to see if you can separate the mud, the noise, from the gold as water runs through your hand. In Illinois, which is in the middle of the cornfield, that is not so well understood. So mathematically, what you do is you create a filter, a model, for what you think the signal looks like, and then you do some data analysis. You cross-correlate your filters against the data, exploring what we call the likelihood function. So the likelihood function, channeling an Australian physicist, is nothing but your noise model. And your noise model is supposed to be, or is assumed to be stationary and Gaussian. And this is an inner product here between your signal and your model. This tilde stands for the Fourier transform of your signal. This is a representation of the noise in your instrument, the spectral noise sensitive curve. This is a Fourier transform of your model. And as you can see, it depends on some parameters, lambda. How many parameters? It depends on the thing you think produces the gravitational waves. The most generic binary system will have many, many parameters. Depending how you count, something like 18, 19 parameters. And so it's a very high dimensional space. So you obviously you do not grid that space, because then you would take Hubble time for your calculations to end. Instead, you explore this likelihood function, trying to map out all of the maxima, all of the minima in some sort of stochastic way. And there's different methods to do that. The ones that I prefer are Markov chain Monte Carlo techniques that use parallel tempering and other things. Another method that does equally well and used properly is nested sampling. I'm not going to get into those here. But what I want to show you is a two-dimensional subspace, so a submanifold, if you want, of this 17-dimensional space. Okay, because you can't visualize a 17-dimensional, it's too hard. So they just project onto 2 dimensions. And so I'm going to show you here the luminosity distance is one of the parameters in your model, and the chirp mass. You think this is roughly the total mass of your binary system. And what you see here is a synthetic data set. So I know exactly what the luminosity distance was for this, because I made it up. And I know exactly what the mass was, okay? And that's this star over here. And so that corresponds to this line over here, and that corresponds to this line over here. So over here, you see what we call the marginalized posterior distribution of the chirp mass, the marginalized posterior distribution of the luminosity distance, and the two-dimensional posterior distribution of the chirp mass and the luminosity distance. That's an example of a very tiny corner plot. If you have more parameters, it becomes a much bigger matrix. So what we're going to now do is we're going to pick different points in the L and M. I'm going to calculate this thing, and based on what I get here, I will decide, and something else that we do to decide whether we jump or not, we're going to jump onto different points on parameter space. Okay? We typically do this through something called the Metropolis-Hastings algorithm. And what I'm going to show you is a movie that Rohit, a former grad student, did as a postdoc at CITA. I'm going to dynamically, in real time, produce a histogram of this, so that you can see that as I try more and more points in parameter space, I begin to build a posterior probability distribution for the most likely value of the parameters that are contained in the data. Okay, so here we go. This is going to go slowly at first, and then we're going to speed up the calculation a lot so that you can see sort of the final answer. You see the histograms are beginning to be built. Sorry, I said that wrong. So the star here, I think corresponds to the maximum likelihood point, not the injection, and the red lines correspond to the injection. So we got that one first. So you see here, like at the end of the day, once your chains have converged sufficiently and you have sufficiently enough independent samples, and you get posterior distributions that match your injection. And so hopefully it's clear that how well you can extract information from the data depends on how good your model is. If your model is inaccurate, then you might get confused and extract the wrong parameters. You might have a systematic bias, and you might actually leave some signal behind. So this is why people have spent the last 60 years or so, way before I even started thinking about doing physics, constructing waveform models, solving the Einstein equations for a binary system. It's too hard of a problem to do it all at once, so we divide this into an in-spiral regime, a merger regime, and ring-down regime. The in-spiral regime corresponds to the time when the objects are sufficiently far away from each other that their velocity with respect to the speed of light is a small number that you can expand about to solve the Einstein equations perturbatively. Eventually, the objects are so close to each other that you cannot use perturbation theory anymore, even if you go to very high order. And you have to solve the whole problem on clusters of supercomputers. That's the realm of numerical relativity. And then eventually, the two objects merge, and a merged object that's highly deformed forms, and that thing has to relax to its final stationary configuration. It does that through the emission of gravitational waves, and that's the round of the ring down, where we can use, for black hole binaries, black hole perturbation theory, different perturbative theory. And you can then glue these approximations in their overlapping region to construct a uniform in-spiral merger ring down waveform. So have you ever heard of IMR? That's what that stands for. Okay. Now, for this talk, I'm going to be concentrating in the in-spiral region only. Okay, so I'm sorry if what you do is numerical relativity. It's super important. I'm not going to be talking about it. Okay. Now, I said I was going to talk about neutron stars. Let's talk about these different regimes for neutron stars. When the objects are really far away from each other, they don't tidally deform each other because the tidal force goes 1 over separation cubed. So you can treat the objects as spheres, but by Birkhoff's theorem, you should know that the zero gravitational field of a spherically symmetric body can be represented by the field generated by a point particle at the center of that body with a mass equal to the total mass of that body. And so I can represent the motion here as the motion of two test particles. The initial separations at LIGO-6 are about 800 kilometers, the velocities are about 0.1 to roughly 0.3, and I more or less arbitrarily define this region to be between 10 Hertz and 400 Hertz gravitational waves. Temperatures are low. You know, million Kelvin is low temperatures for a neutron star, because the Fermi temperature is much, much larger than that. Eventually, the objects get so close to each other they begin to tidally deform each other, and those tidal deformations will encode what the matter that's inside of these objects is doing. Here, the temperatures increase in principle, and you're talking about velocities between 0.3 and 0.4 of the speed of light, so orbital separations between 70 and 30 kilometers. This entire initial regime takes about 20 minutes inbound, more or less, 15 minutes maybe. This part, going from 70 to 30, it takes like tens of milliseconds. It's much shorter. Okay? So the evolution happens very, very, very slowly initially, and then it sort of speeds up. That's why it chirps up. Okay? Then the objects merge and let there be mess. You know, depending on what collided, you can form a hypermassive neutron star that's supported from gravitational collapse due to differential rotation, or you might directly collapse. Here the temperatures can be of order 100 megaelectronvolts, and eventually the whole thing settles down to its final configuration, this post-merger phase. Okay, so again, this is the part that encodes nuclear physics, because over here you're just treating the objects as test particles. Okay, and for this talk, I'm talking about this particular subregion. Okay, I'm not going to talk about the merger or the post-merger. It's very important, very interesting, but not for this talk.
Can I ask about why the temperature increase as we get closer?
Because it heats up.
Ah.
I will talk about that later, but it starts itself. So how does gravity encode matter? Imagine that you have two neutron stars, blue, okay? And they're moving around each other in a circular orbit. As I said before, the tidal force is essentially, the tidal force in this object due to that object is the difference between the force on one side and the force on the other side. You do a Taylor expansion of that, this goes to 1 over separation cubed. You should have probably done that in undergrad. And so this separation is enormous, so this tidal force is tiny, effectively zero. You can treat the objects as point particles, what I said before. Then, as the objects go around each other, they're emitting gravitational waves. The energy that the waves carry gotta come from somewhere, it comes from the orbit. So the orbit is losing energy in absolute value, which means that the orbit is decaying according to the luminosity in gravitational waves that is being carried away. So the orbit shrinks due to gravitational wave emission, and there you go, it shrunk. Okay? So 20 minutes later, it's much closer. Now what happens? Now the objects are sufficiently close to each other that they do tidally deform. You cannot treat them as point particles, so let me deform them. Look. Okay? They're ellipsoids, more or less. And this tidal deformation requires energy. It takes more energy to support a star that's tidally deformed than it does to support a star that's spherically symmetric. That energy has to come from somewhere. Again, it comes from the orbital energy. Again, the tidal deformation speeds up the spiral. Put another way, there's another effect that you can also think about. This tidal deformation adds a quadrupole moment to the spacetime, these two, and gravitational waves go as the quadrupole moment to the two-time derivatives. So the energy lost to gravitational waves goes as the first-time derivative of the gravitational wave squared, which is the same as the third-time derivative of the quadrupole moment squared. But there's now more quadrupole moment than there was before. So there's more gravitational wave than there was before, and there's more energy that's being lost to gravitational wave than there was before. And again, that energy has to come from the orbit, so again, the whole system speeds up. Or, spirals faster. And so it is in this way that the tidal deformations, which we encode in something called the Love numbers, because there was a guy called Hugh Love who studied tides back in the 1800s or 1900s, in reference to the moon. It turns out the moon also deforms. And so we call those things Love numbers. The one that we typically worry about is so-called the electric tide L equal to a quadrupole tidal deformability or Love number. So you'll see me or hear me say Love number or tidal deformability interchangeably in this talk, but more technically that's what I mean. I mean the quadrupole term, which is the most important one. So let's work out the math. Okay, this is where we go a little bit deeper. Okay, so let's say we have a star A. I don't like it when post-Newtonian people, and I'm one of them, call the stars 1 and 2, because then I find that confusing. So I call them stars A and B. And here's some external universe. I don't know what that external universe is in principle, but I know that it's going to perturb my star. That is going to induce, this external universe is going to produce a quadrupole moment and higher multiple moment deformation onto my star, so it turns into an ellipse. Now, if my external universe is another star, then star B feels this external universe and responds also through a quadrupolar deformation. Okay? So what we call the conservative sector, the acceleration of the orbit, without taking into account any gravitational wave emission, is controlled by the acceleration. It's a formula you should know. Central mass acceleration is given by mass divided by orbital separation, r times n, which is the unit vector that points from A to B. Okay? Now, if you don't have point particles in Newtonian gravity, they have bodies of finite extent with a quadrupolar or higher multipolar deformation, there's a correction to the term you learned in freshman physics, which depends on the quadrupole moment, and it looks like this. These are partial derivatives of this one over our term. These brackets are the symmetric trace-free part of the object. You don't have to worry about that, you know what that is. Now, the quadrupole moment of this object is given by the external universe, or the electric tidal tensor produced by the external universe, which we call Eij. And so the constant of proportionality that tells you how the star responds to an external tidal field is encoded in this lambda parameter. And that's the tidal deformability, as mathematically defined. Now, since I know what the external universe is, it's a neutron star that's moving around in orbit, I can do a post-Newtonian calculation to figure out what this thing is. It turns out to be the mass of the other object times the second derivative of 1 over r, which I can evaluate trivially to get this term. Okay? So now I know what the quadrupole moment is in terms of the mass of my body, how much it deforms, and the thing that's producing the deformation. So all I have to do is I have to plug now this into here to get the acceleration. And so if I do that, and I connect terms, and I assume a circular orbit, I get terms that look like this. So I have a bunch of these dots here, means there's higher post-Newtonian order corrections to this term, higher corrections of order 1 over c squared, 1 over c to the 4, and so on, that correct the point particle behavior. Okay? So the first term that corrects, that introduces the finite size effects is this, but there's of course others that are higher order neglected those. That's what the dots mean. And the same thing here. Here there are post-Newtonian corrections to the point particle approximation, and then this is the first finite size correction. Because there's two quadrupole moments due to this star and this star, you get the total deformability of star A and the total deformability of star B in your acceleration. So the orbital energy, which you can calculate by requiring that this energy corresponds to this acceleration, from the point of view of a potential, it's going to be given by this, where this eta is the so-called symmetric mass ratio, m is the total mass, in case I didn't mention it. The symmetric mass ratio is essentially like the reduced mass, and then you have this correction again, which is finite size effects. And you see that this total deformability becomes encoded in this conservative motion, in exactly the shape of the circular orbit. Okay? And moreover, it produces a smaller orbital energy due to the total deformations, or due to the effect that I explained earlier. It takes energy to deform and sustain the deformation. Now, there's not just a conservative sector. If the stars are just always moving in a circle, and the orbit's never decaying, then the frequency is never changing, and then the gravitational waves would be monochromatic, a single frequency, and everything would be entirely too boring for us to care. Forgot I'm getting recorded. Some people would still care. But there's dissipation, and that's really interesting, and you have to model that. There's a lot of energy that's being carried away by gravitational waves. This is the formula that I mentioned earlier. E dot, the amount of energy carried by gravitational wave. The current gravitational wave goes as h dot square, which is essentially the third time derivative of the quadrupole moment square, plus high order terms, like that. But now, the orbit is not just given, the quadrupole moment of the orbit is not just given by the quadrupole moment of having 2 point particles moving around each other, it's also acquiring corrections due to the intrinsic quadrupole deformations of each of the bodies, which remember, we had already calculated in the previous slide. So putting this whole thing over here twice, taking 6 time derivatives, and simplifying, believe me, you get this, okay? And so this is the usual standard result of general relativity. These are the post-Newtonian order corrections, and these are the corrections due to the finite size effects of the orbit. So the total deformability becomes encoded in the dissipative motion, and it leads to more energy radiated due to the tidal deformations. Again, it speeds up the orbit. And so what we care about, of course, is the gravitational wave phase evolution in the Fourier domain, because data analysis just happens to be easier when you work in the Fourier domain for reasons related to the noise. And you can derive a formula that tells you that the second frequency derivative of the Fourier phase is given by the derivative of the total energy, the conservative sector, with respect to frequency, divided by the flux here in the denominator. And both of these things have finite size effects. And so when you plug this formula and the previous one, you take a derivative in here, and you integrate twice, you get this effect, or you get this expression, where this is an overall phase constant, this is an overall time constant. It's 2 time derivatives, 2 frequency derivatives, remember? And then you have all of the terms induced by dissipation, by orbital energy. This is the leading order term for the gravitational wave phase. Depends on the mass to the 5/3 divided by the symmetric mass ratio. This particular combination is related to the Chirp mass. This is why we use the Chirp mass. Then you have post-Newtonian corrections, and now you have this thing. This thing, this term, is what encodes all of these finite size effects. And it leads to less gravitational wave cycles than if lambda were 0, if you have point particles. Okay? And this lambda is a function of lambda A, lambda B, MA, and NP. I didn't write it down. Some combination. Okay? Cool. Great. So if I can go and measure what that love number is from my gravitational waves, I'm in business because I can tell you what's inside of a neutron star. What you would hope.
So Nico, can I say something?
Yeah.
So you're talking about these like static love numbers, it sounds like.
Yes.
But also there's, dynamical love numbers.
We'll get there.
Oh yeah, okay.
I'm just doing the east part first. This was the easy part. So we don't really know what's inside of a neutron star. We think we more or less understand the outer crust, but then as you go deeper and deeper inside, you can have other degrees of freedom that become energetically favorable, like the formation of hyperons or the formation of kaons. Ion exchange becomes important. There could be dragons in there, who knows. But the point is that what you put in here will affect what your prediction is for the tidal deformability. Tidal deformability is a number, but it's a number that depends on the equation of state and the central density of that star. How do you do that? Well, you have to perturb the Einstein equations, some background plus h alpha beta, with some stress energy tensors, the background h alpha beta. The background satisfies the TOV equations for a perfect fluid, and the linearized Einstein equations, believe me when I tell you, can be decoupled into one equation, beautiful equation for a quantity called y, and that quantity called y is just a function of the radial part of the TT component of this metric perturbation. Okay? These f of r and q of r are functions of r only. They depend on the energy density, on the pressure, and the speed of sound of the fluid. That's where the equation of state gets encoded. Okay? If I pick a different equation of state, relation between epsilon and p would be different, and I would get different functions f and q here. The love number then is just given by this beautiful formula that Aina Flanagan and Tanya Hinder calculated, which tells you that big lambda is just a function of something called the compactness, which is the mass divided by the radius of the star, and this function y evaluated at the surface of the star. So all you have to do if you want to predict what the love number is solve the linearized Einstein equations with the right boundary conditions once you've chosen an equation of state, and then evaluate that solution at the surface, plug it into here, and now you have lambda, in principle, as a function of the compactness, or as a function of the mass of the stellar sequence that you're considering. Okay. What does that look like? Well, the mass-radius relations look like this. Sarah showed something like this before for a regular star. Things were cubic for her. This is a lot more interesting because it's not cubic. Okay? So the mass for a neutron star, as you increase the central density, the mass increases, but the radius changes very little. This is quite characteristic of a ton of different equations of state. And that had to do with the fact that these stars are being supported by the degeneracy pressure, okay, instead of radiative transfer. And so you see here a ton of different equations of state that people construct because nobody knows what happens in here, so different people have different guesses on how to model that. And depending on what you guess here, you're going to get different curves. Every point here corresponds to a different star of a different mass and a different radius, and therefore a different central density. So what does the love number of the tidal deformability as a function of mass look like? It sort of looks like this. Fewer set of equations of state here, but still you see a range of values with variability induced by what equations of state you pick. So this is great, because if I can go and I can measure the mass of a star, and I can measure lambda, then that gives me a point in this plane, and allows me to separate and say, well, okay, the star I detected is consistent with this equation of state, or with that equation of state, or something like that. Typically, people like to do, or the way people like to think about this. So a logical argument emerges, gravitational waves encode the love number, or the tidal deformability, and the love number depends on what you put inside of the neutron star. So, the gravitational waves encode what's inside of the neutron star. It's a leap of faith. Unfortunately, however, the waves are sensitive to a particular combination of this love number. So what you measure is not lambda 1 and lambda 2 directly, but it's this lambda bar, it's shear tidal deformability, which depends on the tidal deformability of the two stars, some combination, and the masses. So that's a bit of a problem, because it introduces a degeneracy. How do I go back to measuring M1 and M2, inferring those quantities, if what I measure is just the lambda bar? So let me just take a little detour into universal relations. A long time ago, I was in a place called Montana State University with a postdoc called Kejagi, and we were looking at tests of GR because that's what I cared about at the time. And we're looking at ways in which we test general relativity of neutron stars. The same problem of degeneracy arises there. How do you know that the modification to your observable is due to a modification of gravity and not due to a modification to your equation of state? You don't know what the equation of state is. When people are writing papers saying like, oh, you see, my mass radius curve is different in this modified theory of gravity when I pick this equation of state. And I kept on getting annoyed about that. So I thought, well, maybe there's a way to do a test of GR in a more EOS insensitive way. And so, as we were plotting different things, one day, my postdoc, Kent, shows me a plot where he had decided to plot the moment of inertia, normalized by the mass, as a function of this tidal deformability, this dimensionless tidal deformability. And I totally expected that for some equation of state, you would get a line, for another equation of state, you would get another line, and for a third equation of state, you would get another line. These would all be different lines, and it would be, the relation between I and lambda would be totally dependent on the equation of state. And then what he showed me looked like this. And I said, you obviously made a mistake. There must be a bug in the code. He then reminded me that the code was my code, which then made me think that maybe there was a mistake in how he was running my code. Then I ran my code. There was no mistake in the way he was running my code, so then we did a bunch of analytic calculations. And everything we did continued to show universality. As far as I know, these are some of the most insensitive relations that you can construct between the normalized moment of inertia, the lab number, and the spin-induced or rotation-induced dimensionless quantum moment. What you see here are a bunch of different equations of state and sequences of energy densities for different stable regions of neutron stars within this set of equations of state, as well as here. The black line is what you get when you take all of those data points and you say they all come from the same data, and I'm just going to construct an average. Okay? And then what I'm going to do is I'm going to take each of those points and I'm going to take the difference between that fit and the data divided by the fit, so as I can see the variability of these points with respect to that line. And the points don't lie on top of the line. They look like they do because the symbols are large. This is achieved. Okay? There's variability at the order of 1% or so, 2%. Cool. So it looks like this moment of inertia quantum moment and lab number satisfy approximately universal relations. We then looked at certain combinations of the tidal deformabilities, and we found that those also satisfy approximately universal relations that also happen to depend on the mass ratio. Right. So the tidal lab numbers also satisfy the EOS insensitive relations, not as good as the previous ones, which is a variability of like 10%, but still they're approximately universal. Now before you ask, why do these relations exist? I get this question every time I present my previous slides. So I'm going to tell you what does not explain the universality. So one statement is, oh, this is because all of the equations of state that you've looked at are all similar to each other. The answer is no. You can consider changes that are 30% in the equation of state that lead to changes in the mass radius curve that are 20%, but changes in the eigenvalue relations are less than 1%. Okay? Universality is because these are all neutron stars, so they're all very simple. No. The universality remains if you consider rapidly rotating stars, if you consider differentially rotating stars, and even if you consider magnetized stars. Unless these magnetized stars are like true magnetars, and the magnetic fields are like 10 to the 15 gauss, and then the quadrupole moment acquires a contribution due to the magnetic field, and then that depends on the geometry of the magnetic field. All the universality is because you don't consider questions like the phase transitions. Surely phase transitions lead to this crazy twin star, like to work on. No, even if you consider those, this universality seems to remain in the I love Q relations. Okay. Okay. So the explanation I like is the following, which is not ironclad, but it's what we have right now. Consider the phase space where all possible stars live. You can imagine an effective polytropic index in this axis, the ratio of the temperature to the Fermi temperature on this axis, or the variation in the eccentricity profile, like how elliptic the star is, or the compactness in this axis. So stars are not very compact. With large polytropic indices, they typically live over here. As you consider more compact stars, you move up in compactness. Neutron stars are somewhere over here, and black holes are like over there at some point. Okay. So now consider flowing from here to here along some trajectory. And so what you find is there's some sort of effacement of these microscopical or microphysical properties. The equations of state become increasingly barotropic, up until the point where you consider neutron stars, where we just assume they're barotropic. The vorticity is not sourced, so the stars are believed to be in rigid rotation. They're old. Okay? And when that's the case, Dong Lai at Cornell and Stu Shapiro back in the 80s proved that the energy configuration, or the matter, the density configuration that minimizes the energy, happens to be isodensity contours that are nested with respect to each other. They might not be circular isodensity contours, they might not be two spheres, they might be ellipsoids, but they're still nested, and there is a self-similarity in these contours as you go in. And this self-similarity gets better and better and better as you go to more and more and more compact stars. So one possible explanation is that as you move from here to here, this symmetry begins to slowly, spontaneously arise, giving rise to this universality density. Okay. Has this been proven at the level of the Hamiltonian, at the level of an order parameter, or something like that in physics? That's what we know. It's very hard to do that, but it's a possibility. Okay, so now that we understand universal relations, let's go back to trying to extract physics from gravitational waves. So remember this argument? Gravitational waves encode what's inside, but what we measure is this combination of lab numbers. Okay, but now I told you that there's a universal relation between the difference in the total deformabilities and the sum of the total deformabilities, and it's analytic. Okay, so then you can use I can use this relationship in here and rewrite these two terms entirely in terms of just lambda s. And if I do that, if I have a measurement of delta psi, effectively you can think that you can measure lambda s. And once you have lambda s, I'll do you one better. I can plug that lambda s that I just measured back into here to measure lambda a. And once I have lambda a and lambda s, I can use the inverse relation to extract lambda 1 and lambda 2. Because lambda 1 is just the sum of lambda s and lambda a, and lambda 2 is just the difference of lambda a and lambda s. And once you have that, you have the lab numbers of each individual star. And now you can do this test that I mentioned earlier. You have to be more careful than that because these things are not perfectly universal. There's variability of the order of 10%, and so you have to fold that in when you do the data analysis and marginalize for that systematic error, which is something that people in the language collaboration did. Karina Hatsuano was one of the people that worked on this back in the day. And this is what you get when you construct the marginalized posterior in the mass radius plane using these universal relations. These are, the color just stands for the marginalized posterior distribution, so darker means higher and lighter means less high. These lines here mean think 60% contours and 90% contours or something like that. You have two of them because you have two stars. And what you see here is the marginalized posterior for the mass and the marginalized posterior for the radius, sort of like a corner plot. And what you see here are the mass radius curves for different equations of state. So this is one of like the most, one of the earliest studies, and today one of the most primitive studies to get information about the equation of state. What people said at the time is like, oh look, this line here is less supported by the data than these lines here, because there are central densities for which you can produce the stars that LIGO saw for these equations of state, but not for this equation of state. Okay. Today, we do this in a much better way. There are other ways that Reed, for example, has pioneered on how to draw inference from the equation of state. We have the expert here. I'm sure he's given you at least 5 talks on this, so I'm not going to describe. Okay. Let's go beyond the radius, right? We were talking about like, oh, measuring the mass, measuring the radius, the equation of state, the relationship between pressure and density. But the equation of state, if you look at nuclear physics models, they can be very complicated. Equations of state cannot be calculated analytically, they have to be calculated numerically by solving different sets of equations for many-body systems. And a thing people like to plot is the speed of sound square, which is the ratio between, the derivative of the pressure with respect to energy density. And so when these quantities are approximately 0 in some range of n, we say that there is a first-order phase transition, which could signal the appearance of strange quarks or some new phase of matters and new particular freedom. We can also have high-order phase transitions that do not require this to be 0, but can introduce like bumps or plateaus and so on. Here are some examples. The green line, it's called the Sly equation of state, is what pretty much everyone assumed an equation of state would be like in 2008. Mostly because that's what we were familiar with in the gravitational wave literature. Meanwhile, simultaneously and in parallel and without talking to each other, the nuclear physics community was producing all these equations of state you see here in other colors, which look nothing like the green line. It has bumps, it has kinks, it has plateaus, it has all sorts of craziness, and there's rich physics in that structure. So the question is, can you pull that structure out? After all, this is the speed of sound squared, and this, in some sense, there's like an integral that you have to do over quantities that involve this to get the observables that you see. You don't measure CS squared directly. You sort of measure some byproduct of CS squared. And the answer is yes. Here are different CS squares that we concocted by hand. We studied a bunch of them. Here are different pressure versus density. When you integrate these curves, you see visible changes in P versus epsilon. And you see very large changes in the mass radius curves as you introduce this structure, as well as in lambda m. And lambda m and m and r, these are things we do measure. So then the hope is that by measuring these quantities, we can do the backward problem and infer something about CS squared, or higher derivatives called susceptibilities. Okay? But we can do one better. So far, we have assumed that everything is in equilibrium. So to answer Neil's question, everything is static, right? We've said the tidal response of a neutron star can be Taylor expanded about small frequency. If you think about it in the frequency domain, and the first term in the frequency domain in the Taylor expansion, about omega equals 0, is a constant, so it's stationary. Then you have a linear term in omega, then you have a quadratic term in omega, and so on. Up until now, we've always discarded the linear term in omega because it's odd under time reversal. It's odd under t, which means, right, because it's linear, which means it's a dissipative term. And we've always thought there is no dissipation in neutron stars. So we only included the omega squared term. The omega squared term, when added to the response, leads to the possibility of exciting a simple harmonic oscillator type motion between that it essentially excites these F modes, or these other astroseismological modes in the neutron star. And those can become resonant with the orbital frequency and lead to a huge effect, like epsilon away from them merging. Like this F mode frequencies are very high. But what about the linear term in omega? So I'm not going to talk about further about dynamical tides. Let me just talk about the linear term in omega that we've always set to 0. Well, when the neutrons, let's imagine you have a neutron star, it's very cold. They just say, for kids, when I teach a class of neutron stars, which I'm doing right now, it's just a ball of neutrons, protons, and electrons. It's a simple model, okay? And some low temperature. And so if you have that, the mean free path of neutrinos is much, much larger than the radius of the neutron star. So any neutrino that gets produced will just like fly out of the neutron star. Okay, the temperature is low. So if the star is isolated, there's this awesome process called the Urca process. You know why it's called the Urca process? You ever heard of this? Okay, do you know what this process is? It's like beta decay, inverse beta decay. It's happening constantly. And this is what leads to chemical equilibration in a star. Okay? It's called Urca because the people that came up with that were in a casino in Brazil. It was related to Urca, and this process led to a loss of neutrinos in the star, just like you lose money when you enter a casino. That's the story. They're making a face, but it's true, it's in Wikipedia. I'm just repeating what I heard in Wikipedia. But now, if you put this star not in isolation, but now in presence of an external universe, I'm the external universe, I'm pulling on that star, so I'm deforming that star. Now, there's a time scale for hydrodynamical perturbations, oscillations in the baryon density. So your little fluid element that had like one electron and one proton and one neutron, now all of a sudden acquired a new proton, let's say, because the star stretched, it moved. That timescale now begins to compete with this timescale for system equilibration via nuclear processes. Okay? And so if this hydrodynamic timescale is very, very large with respect to the nuclear timescale, so the nuclear reactions are happening super, super fast, then it doesn't matter, right? Everything gets instantaneously equilibrated by nuclear reactions. Like if the proton happens to enter your little fluid ball, poof, instantaneously it does this, and then it equilibrates, okay? If, on the other hand, the hydrodynamical timescale is very, very short, so it takes forever for a nuclear reaction to happen, then it's like there are no nuclear reactions, you remain in this unequilibrated state, you just merge, okay? But if these two timescales become comparable, then the nuclear reactions will try to change the composition to try to equilibrate, but there won't be enough time for that equilibration to happen. So you're going to have a net gain of entropy. Every process here adds entropy, the neutrinos remove entropy, but more entropy is being generated by the processes that there's time for the neutrinos to escape and like remove the entropy. So you have this net entropy gain, which leads to what we call an effective viscosity. Why? Because the divergence of the entropy current can be modeled as a viscous process. This was proposed by Noronha and other students of his who are all nuclear physicists. And so the idea is that this out of equilibrium nuclear process, or Mark Alford and others, out of equilibrium nuclear processes generate this effective viscosity neutrons. Okay, how big is it? We don't know. Okay, but if it is there from an observational point of view, so I'm going to put my observer's hat now instead of my mathematician's hat. What is the effect of this in the thing I measure? That's what I want to answer.
What do you mean you don't know?
I have to calculate.
Yes, but it's eminently calculable.
It's eminently calculable.
Or, you know,
We are doing the calculation and we don't quite know yet. You have to put in a finite temperature equation of states, and you have to solve the linear perturbed Einstein equations with a particular divergence for your entropy current that has reaction rates.
but local result the
The reaction rates have locally been calculated. Yes, that's what allows me to do the calculation that I do.
okay. I see. Embedding it in GR hydro, that's not complete.
No, it can be done, it just not yet.
I understood. Thank you.
Okay, so how does this change things? Well, remember I told you these two stars get deformed around each other. If you have viscosity, what now happens is that the dissipation induces a tidal lag, which creates a tidal angle, or a lag angle, between the line pointing along the bulge and the line pointing between the central mass of the two bodies. Tidal lag is something we are all familiar with from the motion of the moon and the Earth. If you have a tidal lag, then this tidal lag will end up torquing the binary, which ends up speeding up the inspiral further. If it speeds up the inspiral, it changes the orbital motion. If it changes the orbital motion, it changes the gravitational waves. So this tidal angle gets encoded into the gravitational waves emitted. We've done the calculation. You should recognize this from a previous slide. This term was presented before. These terms are new. And what I want you to notice is that these terms here scale as pi mf to the 8/3. By Kepler's law, believe me when I tell you that pi mf to the 1/3 is like v over c. So this is like v over c to the 8, this is like v over c to the 10, and this is like v over c to the 10. And what is v over c for a neutron star? At most 0.3, 0.35, something like that, so it's smaller than 1. So this is smaller than this. And this, I told you earlier, we think we can sort of constrain or measure with GW 17917. So if we can see this, in principle, if C bar and delta C bar are large enough, we should be able to see that. Okay? And that's exactly what we did. I mean, you can then relate, running out of time, so I'm going to skip this part, but you can relate what this C bar is in terms of viscosity, the average kinetic viscosity, then skip that. This is what you get when you analyze the GW 17917 data for the posterior on this C1 and C2. The green and the red are the marginalized posterior distributions after varying of all the parameters. I'm just showing you this one-dimensional submanifold. This line here is the prior. It's what we assumed initially these things were before the analysis. Prior, very different from the posterior. We have gained information, and the information we have gained is that if this C things, if this dissipation is present in the neutron star, it's smaller than this number. Okay? And so now the question is, how does that map to the physics that's encoded in the equations of state, the finite temperature part of the equation of state, the reaction rates that are sourcing the current in the entropy, that are sourcing the entropy current. And the answer is, we don't know, we're doing the calculation. Stay tuned. But it's interesting, because it's a new avenue into nuclear physics that have been overlooked until now. So what's next? I'll conclude with an optimistic note. We're going to get much more sensitive detectors. O5 will detect 100 different neutron stars, right? And then after O5, maybe 5. After O5, we will hopefully have an improved detector. People are talking about something called a shark. Other people are talking about even more sophisticated things like Voyager. In the long term, in the 2030s or so, people are talking about a cosmic explorer, an Einstein telescope, which is third-generation detectors. But for sure, what we know is that this is not the end of the gravitational wave story. More detections are coming, and some of those are going to be at very large signal-to-noise ratios. If we had detected GW 17917 today with O4 sensitivity, the SNR would have been like 9, I think, more or less. Sure. So once we have that, would we be able to measure structure in the speed of sound? Can we measure these out of equilibrium processes? Will the posterior spike away from 0 and allow us to infer something interesting instead of an upper limit? And can we parameterize the nuclear physics directly? So I'm the PI of a cyber infrastructure team called the MUSIS team, which is doing precisely that. We are constructing this global equation of state that should work in the QCD phase space. so that we can then do parameter estimation directly in terms of the nuclear physics parameters that appear in those wonky equations of state that I showed you earlier. Can we do that directly? Are we going to have to use emulator or some sort of neural network to emulate those equations of state? That remains to be seen. But I think the future is for sure very interesting. So I'll stop there.
Okay, Nico, thank you for the awesome talk. I'm just gonna, we have some questions here. So just a quick question from online.
Well, I had just a question that's less tangential.
Okay.
Could you go back to the slide where you showed the, I forget what the Greek letter is, but you know, lambda and c. Yeah. Just give us a sense, a very simple, you know, equation of state, say, you know, even ideal gas equation of state. What the magnitude of c and is relative to lambda?
Right. So lambda, this dimension is lambda 1, like for one of the stars, varies between roughly about 10 for the very, very massive stars to roughly, like, say, 1,000 for the very, very light stars. And it's more or less independent of the equation of state. When you plot lambda as a function of mass, it decays when mass goes that way, it decays like this. I should have plotted that earlier. And it's between 1,000 and 10. Why? Because, well, it's very simple. Like the lower the mass, the more fluffy the star is, so the more easily
High
deformed.
power of mass. Exactly. But then.
And now the c, that we're in the process of calculating. Some estimates of this tell us that this could be anywhere from, again, order 10 to order 5,000. And we don't know exactly where in that range is, or how it scales with mass, or how it scales with temperature, because we haven't quite done the calculation. If the temperature were very, very low, then this c would be very, very low. Right? And so it depends on what the temperature is in these last stages of entropy, and goes to your question, right? As the neutron stars are producing this entropy, they are heating up very slowly. And so we know that at merger, the temperature is about 50 MeV. But we don't know before merger what the temperature is. We know when they're isolated, they're about 10 to the 6 Kelvin. And so we are doing that calculation too to try to figure out.
Well, actually, the question we also be, I mean, what's the current range of results for the temperature increase due to, you know, mode excitation? Even if the mode excitation isn't significantly affecting the phase as it could, it's significantly affecting temperature.
Yeah, I don't have a number in Kelvin for you. I mean, I think what Nico said is about right. The question is fundamentally boils down to how much energy you can dump into those modes, and then if you assume that all of that energy thermalizes, it's usually a relatively small fraction of the binding energy of the star that you could possibly excite with these modes.
That's what this.
So binding energy is huge. So
Yeah. So, but like I don't think that I think that the lore is that you do not expect to significantly heat up the star.
So in relative to 10 to 6, you're actually not.
You're probably not going to bump it up to 10 to the 8. I don't think it's. I mean, it would be.
That's interesting because the rest of the equivalent goes as t squared, so that's a pretty substantial amount.
Yeah.
So we know that when it merges, Urbana simulations show that temperature goes up to 50 MeV.
Sure, when really
Once
sheer
the
thing
thing has merged. So we know that the energy is definitely below 50. And how much below 50 it is, it remains. I think that's the question.
We did have a question online about R modes. So the question was, do the distributive effects connect to R modes, and would you be able to see the properties of exciting R modes?
Yeah. So R modes, for people who don't know, are rotational modes in a neutron star that have to do with the Coriolis force, the difference between frames, co-rotating observer and inertial observer phenomena. Very interesting. They go through these cycles where they can potentially grow then they get quite by nonlinear effects, and then they may go again. There's something called the CFS stability for trying to cycle failure shoots. Anyway, very cool modes. Those have always been studied in the absence of dissipation, as well as F modes for that matter, and G modes and so on. And so if there is this kind of dissipation, effective viscosity in the neutron stars, then for sure those are going to get affected. And so I went to Tübingen to talk to Kostas Kokotas specifically about this, because he's one of the world experts on astroseismology. I'm looking at you because I don't know who to look at. I guess over there. And so there's a postdoc right now that is working on that precise problem, enhancing those calculations, numerical relativity calculations, to include these dissipative processes. So, like from the dynamical type point of view, your simple harmonic oscillator becomes a counter-simple harmonic oscillator, and then you won't reach resonance, for example. So inferences that you can make based on, oh, I didn't hit resonance because I didn't see it, then this means X or Y in terms of the F modes or in terms of equations of state, are sort of not so straightforward because of this degeneracy in the damping.
Other questions for Nico?
So for the sensitive tidal correction, does this only really matter when you're in a specific in-spiral frequency where it's comparable to the nuclear timescale?
Yes.
And then in that case, can you map out, I guess, the flux as a function of the in-spiral frequency, and then that lets you tease out more between the conservative tidal correction versus the sensitive tidal correction?
So I guess the last part, but for sure, this effect only matters when the tidal deformations start changing the chemical composition of the star. That happens at higher frequencies. So definitely need the orbital frequency to be larger than, sorry, the gravitational wave frequency to be larger than 400 hertz. Separation smaller than 100 kilometers. Now the nuclear time scale is not so easy to calculate. It depends sensitively on the temperature, depends sensitively on the baryon density. So therefore it's not constant. It's not the same from fluid element to fluid element inside the star. The star is going to 5 different orders of magnitude in baryon density from the core to the center. So a lot more work still, I think, needs to be done to understand exactly how the dissipative probability depends on the time scales and on the temperature. We're working on that.
Any other questions?
So a lot of the parameters, like these come purely from the gravitational wave detection. Is there anything from the time domain electrodynamics in this spectrum to help?
Yes, that's a great question. So I was recently working a lot with Macarena Lagos, who's now a professor in Chile. Who was at Chicago with Leah James, and precisely that, right? So awareness. How much information, well, how much do we gain by combining the information we learned from the electromagnetic current? So what do we learn from the electromagnetic current? We learned the distance, because we have galaxy identification, as I mentioned. We learned roughly the inclination angle, because we saw the GRE, and so the opening angle would be much larger than 30 degrees. And then we learned a bunch of other things related to the remnant in terms of the kilonumber, but that doesn't quite matter at the level of the experiment. Now, all of those parameters I mentioned, velocity, distance, redshift, and inclination angle, enter predominantly in the amplitude of the gravitational wave. And everything that I have mentioned so far enters the phase of the gravitational wave. Meaning it also enters the amplitude, but detectors are interferometers. And they are much more sensitive to the phase evolution than to the amplitude evolution. So the modifications due to the tidal dissipation introduced into the amplitude are greatly subdominant relative to the modifications that introduced into the phase. And once again, observation gives us this more information about the amplitude. So no, unfortunately, it doesn't really happen.
Well, let's thank Nico again. cookies and refreshments upstairs, so if you think of other questions, you can corner Nico. At least give him a cookie first, but then continue that. All right. Thanks, Nico.
Thank you.